Hey guys and gals, we're back, and today is a big day. Today we're going to be putting everything together that we've been working on over the last few weeks. All right, so what we're going to be doing is we're going to try to find the equations for linear functions from tables, graphs, and word problems. All right, so we're going to take pretty much everything we've done. So if we go back, we need to know things like what is a function. We've got to be able to find things like slope, things like our y-intercept. We also need to know things like slope, intercept, form, and the difference between dependent and independent variables. We're going to put all of that together now to be able to go back and forth, so to speak, between the geometric and the algebraic. So let me show you what we're talking about. When we want to write an equation, so for example, let's just write out a very simple equation here, something like y equals, I don't know, 2x plus 1, right? If we want to be able to generate an equation like that for an actual situation, then here's what we need, all right? Here's the key information that we're going to need to do what we need to do. First, we need to know what are the independent and dependent variables. Remember, the independent variable is what is going to cause change in the dependent. We said that independent variables a lot of times tend to be measures of time. Maybe we're talking about how many minutes have passed and how many students have walked into the gym for the dance. Independent quantities, all right, are things that we will put in. So, for example, we said that it was our input, all right, that kind of thing. Dependent, all right, dependent situations are the output. Typically, that's one word, but I ran out of space. Again, this is typically what we're looking for. So sometimes we can think of it this way. A lot of times, not always, but a lot of times our independent is what is known and our dependent is what we're trying to find. Right? So for example, if I know how much time has passed, how many students will there be? Or if I know particular input, maybe how tall I am, then the output would be, well, if I know my height, then maybe I could guess my weight, that kind of thing. Right? So we need to know what's input, what's output, or independent and dependent. We also need to know what is the rate of change, okay? Or another word that we have used in here is slope, right? And again, those words are interchangeable. But how does our situation change? We need to know that. And then finally, what is the initial value? And again, the word that we've also used for that is y-intercept. So for example, if we look at this situation, our x, maybe that is the number of minutes, all right, that have passed. Maybe the 2 represents that, every minute we're going to have 2 new students walk into the gym. Maybe there's a school dance or something. So this would be our rate. The 1 would represent our y-intercept. So maybe we've already got 1 student in the gym. Maybe they stayed after school to help decorate or something. Who knows? And then our y would be our output, in this case, the number of students that we have at the gym. All right? Put in sort of a more general way, because that was a very specific example. Put another way, if we want to write our equation out, it's going to look something like this, in what we call slope-intercept form. Now, there are other ways to write linear functions out, but this is the one that we're going to be using this year, and you're going to use this format for at least algebra, geometry. It won't be till really algebra 2 that you're going to start meddling with those other formats real hot and heavy. For our purposes, this is going to work. So again, a general idea of where things go. Again, the b represents the initial value, or that y-intercept. The x represents the independent value, or our input. Right? Whereas m represents our rate of change, or slope. Initial value, I forgot to mention, y-intercept. And then dependent, again, this is what we're typically getting out, or what we're trying to find. So output. Right? So long as we can get our equations in this format, we'll be doing good. Because there's a lot we can do with it. Remember we said we could use initial values and slopes to graph it. We could use this equation to find specific information. For example, up here, let's suppose that 10 minutes have passed. Well, if I take 10 and put it in, 10 minutes have passed, 10 times 2 is 20. Plus 1 is 21, so that means, hey, there are now 21 students in the gym. So we can use these to, say, predict future events, things that we aren't sure about yet, but our function could help us predict. So let's take a look here. We'll work through some examples and see how we can generate these equations. All right, so take a look. First one, we need to write the equation for the function represented by the table below. So let's look at the table first before we get into our questions. Let's see, home football game gate money. So gate money refers to all the money that's collected as people come in for the fans. Speaking of which, we've got one column here that represents the number of fans. So if no fans showed up, or 10, 20, 30, and obviously we could make that continue. And then gate money collected. So we've got 500, 650, and so on. So the first question we have, what are the independent and dependent variables? And remember, typically, not always, but typically we represent our independent variables with x and our dependent variables with y. But we certainly don't have to, and I can show you that here in just a second. But for now, we'll keep it x and y since that's what we've done. So the question is, will the number of fans determine how much money we end up with, or does the number of money determine how much fans we will see in the stands? Well, in this case, it's pretty obvious. However many fans show up, that's the money we're going to get. So our independent, and I'm going to abbreviate here, our independent variable in this case is the number of fans, right? And our dependent is the gate money. Now, let's talk about this. Number of fans would be x. Gate money could be y. However, we could substitute those values for something else, those variables. For example, I could let fans be represented, say, with an f. And the gate money, maybe I represent it with an m. All right, and we'll talk about both versions of this. But for now, let's stick with x and y. But again, I'll show you another version with f and m. It'll be the same thing. First thing we need to do, we need to figure out how this situation changes. So since I don't have a graph that I can count, I'm going to have to use my slope formula. So I'm going to grab these two coordinates here, the ones up top, just because they're the smaller ones, coordinate 1, coordinate 2. So let's find slope, 650. And by now, folks, we should be very comfortable finding slope. So 650 subtract 500 over 10 subtract 0. So in this case, 650 subtract 500, that's 150. 10 subtract 0, that's 10. So it looks like my rate of change is 15. And if we wanted to get specific about what does that mean, then we've got $15 per person. All right, but that is our rate of change, our slope. All right, that looks good. Our initial value, what are we starting with? Well, remember, all initial values are going to start with 0, some number. All right, we're not sure what that number is. We don't really care what that number is, but we have to find it. In this case, the table already gave it to us. At 0 fans, there is $500. So maybe they had another game and they had $500 left over for gate money. Or maybe they keep so much money, though 500 seems like a lot. Maybe they keep so much money for change. You know, they keep it in 1s and 5s, that kind of thing, in case people need change. But they already start without anybody showing up. There's already $500 there. So our initial value, we could say, is at 0, 500. Or again, if we wanted to write out what it meant, we could again say maybe that's $500 in change. Maybe they use that for not only the gate, but maybe the concession stand or whatever. We don't care. So now it's time to put the equation all together. All right, so remember, y equals mx plus b. So the information that we need to substitute in, we know that x represented number of fans, so we'll just leave it x for now. Y represents the gate money, so we know that. M, our slope, is 15. So I'm going to take the m out and put 15 in its place. Let's go ahead and rewrite the x and the y. And then b, our intercept. In this case, we said that we would start at $500 before the game ever begins. And here's our equation. Y equals 15x plus 500. Now, a lot of times people won't use x and y. They'll use other variables, which brings us back to question 1. If we wanted to substitute x's and y's for other variables, we can. So we could rewrite this equation with f being the number of fans. So we could take x out, put f in its place. So I could take the number of fans times 15 plus the $500 we already have. Remember, that was $15 per fan. And that would equal m, the amount of money. So again, we don't have to use x's and y's every time, right? We can use other variables. For the most part, though, I'm going to stick with x's and y's, but just be aware other teachers might use different variables, or other problems that we do might use different variables, and we just need to be comfortable with that. but make certain you let people know what they mean. So just like we did here, that X was fans, Y was money, so that way people know what it represents. All right, let's try another one. Let's see. We got the county pool drain schedule. So maybe when they pull the plug at the end of the summer, they let them know how much water is still left. So we've got number of hours, so 0, 1, 2, and the number of gallons. My goodness, that's a lot of water. And oh goodness, it's not changing by a lot either. So it's probably going to take a long time to get that pool to go down to nothing. So let's see what we've got. What are the independent and dependent variables? Well, again, I noticed that time is one of our measures here. And odds are if we've got time, that's going to be independent. That's not an always situation, but I'd say 9 times out of 10. So in this case, we can say our independent situation is the number of hours, and that our dependent then would be gallons in the pool. Cool. And we'll let that number of hours be X, and we'll let the number of gallons left behind be Y. All right, looks good. First thing we need to do, what's our rate of change? Again, we don't have a graph that we could simply count this off, so we will need to use our slope formula. And since these are big numbers, I've left us some extra space down here. So I'm going to go ahead and grab the first 2 again. Remember, you can grab any 2 coordinates you want, but I'm going to grab the first 2. I think that's going to be easier. So let's write, again, coordinate 1, coordinate 2. We'll just number them off. So let's see, 598,500 gallons, subtract 600,000 gallons. My goodness, that's a lot. All over, let's see here, 1, subtract 0. Oh, goodness. Not sure if I left myself enough space there. Well, let's see. If we go up 1,500, it looks like we would get back there. So negative 1,500. And then, but 1 subtract, well, and there we are. So it looks like our rate of change is just a negative 1,500. So it looks like they're able to take 1,500 gallons out each hour. And that seems like an awful lot, but my goodness, they've got 600,000 gallons they're going to have to get rid of. That's going to take a while. So what's our rate of change? If we were to write it as a number, we could just say that M is equal to negative 1,500. And that's okay for now. However, if we wanted to talk about what it means that we can pump, there we go, I can spell, 1,500 gallons per, make sure I get my time right, hour. Yikes, that's a lot of liquid. All right, cool. So there's that. Now we need the initial value. Notice this table is set up perfectly. We can find that initial value just by looking. Now remember, if we don't know the initial value, let's review real quick the process. First, you need 2 points. All right. Second, get the slope, which notice we've already got. And then our third step, remember, is use y equals mx plus b to find b. So again, just a real quick review of that process, but they've already given it to us. So in this case, the initial value is 0,600,000, or that we simply started with 600,000 gallons of water in the pool. I think that's awful close to Olympic size, if I'm not mistaken. It may be a little short, but about that much water. Cool, so we got all our information. Let's write the equation. So in this case, we're going to write y equals mx plus b. So let's fill in what we know. The slope is 1,500 rather gallons per hour. But remember, we're losing that. All right, the water is leaving the pool, so we need to make sure we write that as a negative. So y equals a negative 1,500x. Remember, x represents the amount of time, hours. So I take the hours, multiply it by negative 1,500, and then we're going to add on the 600,000. That's our y-intercept, our 600,000 that we start with. So for every hour, we're going to lose that much. So the more time that passes, the smaller, so to speak, that value becomes, and allows us to take away from here until eventually we could whittle it down to the pool being empty. Cool. So again, not a huge, lengthy process, and certainly not a difficult one. But again, there are a set of steps I really would recommend that you follow. All right, so that's a table. Let's try graphs. Graphs are easier simply because it's a little more visual and we can see what it is that we need to do. So let's start with this one. This is just a random graph I put together. The x's and y's really don't mean anything. So what are the independent and dependent variables? Well, we can make that simple. Independent will be x and dependent will be y. Notice we don't have any labels here, so we don't know what we're really measuring, and that's okay. What's the rate of change? Well, notice since we've got our graph, we can go ahead and count from point to point, and that would be a lot easier than using the formula. So in this case, I'm going to count up 1, 2, 3. So our rate looks like it's 3 over, so let's see, we counted 1, 2, 3, and then 1, 2, 3, 4, 5. So it looks like our rate of change is up 3 and over 5. Cool, 3/5 for a slope. Initial value. So where does it cross the y-axis? Well, again, we don't have to look at a table to read it. We don't have to calculate it. It's right there. Excellent. So in this case, our initial value is at 0, -2. And again, since we don't know what we're measuring, we're not sure what these numbers mean. And quite frankly, we don't care. That's just fine. We can still write the equation for this line. So we've got our rate. We've got our initial value. Remember all equations, y equals mx plus b. So let's substitute. Y is, well, y. We don't know what it is and we don't care. Slope, in this case, 3/5 times x. There we go. Plus b, and in this case, it's a -2. So since it's negative, I could write it a couple ways. I could write it simply subtract 2, which I think is a little cleaner. You could also write it as adding -2, and that works as well, though I think that version is a little bit nicer. All right, cool. Well, that was easy enough. Let's try another graph. Let's take a look at it, though. Notice we've got some labels here. We've got sweatshirts sold, all right, and the profit. Okay, so it looks like somebody's selling sweatshirts and trying to make a profit doing it. There's no harm in that. Independent and dependent. Well, independent in this case, remember, is on the x-axis, so sweatshirts would make sense. The sweatshirts are going to tell us how much profit. So again, the independent is the number of sweatshirts. And in this case, that'll be our x. And the dependent will be profit. I'm assuming measured in dollars. And that'll be y. All right, cool. Always want to know what we're measuring to know how the actual function works. What's the rate of change? Well, again, I think it's going to be easier to count this out rather than doing the formula. So let's pick any 2 points. I'm going to grab those 2. So, and notice how we're counting, though. Here across the bottom, we're counting by 2s, but here along the side, so on the x, it's by 2s, by the y, we're counting by 20s. So be careful. We can't just count 1, 2, 3, 4. That's not going to work. So we've got 20, 40, 60, 80. So I'm going to write that down. We went up 80, and then over to 4. Cool. So up 80 over 4. Let's simplify that because we really didn't have a lot of space down here to do our work. See if that can refocus for us. There we go. So 80 over 4 is a fancy way of talking about a slope of 20. So it looks like they're selling each t-shirt $20 per t-shirt. Remember, rates are y over x, dependent over independent. So $20 per sweatshirt. So our rate of change is 20. What's the initial value? Well, I notice on this graph, we can't see it. We would have to extend this line way down here and then bring this down and try to see where they meet. And quite frankly, we don't have time for that. So let's review the process. First, we need to pick 2 points. Well, we kind of did that, all right? So check. Second step, we need to find the slope. We did that. It's 20. Check, all right? Equals 20, not -20. Third step, y equals mx plus b. Let's do that. So y equals mx plus b. M in this case is 20. X, let's pick an x. Well, in this case, I'm going to use this coordinate here. I'm going to use 6, 20, just because the numbers will be small. So the x is a 6, y is 20, and then, of course, we're finding b. All right? Well, 20 times 6 is 120 plus b. And when we subtract 120 from both sides, we're going to get a -100. So our y-intercept is at 0, -100. So in this case, profit being negative, that would mean that, oh, they probably owed money. So maybe they had to buy the t-shirts ahead of time, or maybe they had to pay a fee for printing, whatever. But we could explain what that meant to a certain degree. All right, now we just need the equation. So y equals, we need our slope first. So in this case, $20 per shirt, so 20x. And then since we have a negative intercept, again, we can write it as just subtraction. So subtract 100. And in this case, it looks like it's somewhere between 5 to 6 shirts there where they finally do make a profit, right? Anything before that time, it looks like they still owe money, right? So good. Another way to write out our equations from graphs. Pretty straightforward. And notice it's the same process no matter what we're looking at. All right, well, let's do a couple of word problems, then we'll call it a day. So I'm watching time on the video here, and it's getting a little long. All right, Farmer Brown is trying to plant corn for a new season. He already has 100 acres planted, so that's a good thing. His planter can plant about 15 acres an hour. Cool. Write an equation to represent Farmer Brown's situation. All right, so we got independent and dependent. Well, it looks like we're measuring two things. One is that we're measuring time again. So independent, in this case, probably the amount of hours, in this case, the number of hours, and we'll let that be x. Again, we could represent it with an h if we wanted to, but we'll do x for now. And then our dependent variable, in this case, looks like is the number of acres that are planted. So again, notice here's the rate, acres an hour or acres per hour. We could say it either way. So in this case, dependent is simply the number of acres. And we'll call that y. All right, so rate of change, well, notice they gave it to us. We don't have to go looking. We don't have to go counting. It's already there. So our rate of change is 15, in this case, acres an hour. What's the initial value? So how many acres does Farmer Brown already have in the ground planted? Well, it looks like it says it right here. So again, 0, 100. He's already got 100 acres in the ground. So he's doing pretty good. Where do we go from here? Well, and now it's time to write the equation. We've got all the information we need. We're good to go. So y, in this case, the number of acres that are planted, is equal to our rate. He can go 15 acres an hour, which is pretty darn fast. He must be flying there, times the number of acres. Cool. Added on to the 100 acres that he already has in the ground. So good. He could use this equation provided conditions don't change. Let's say if he has another 8 hours on his hands, he could take that, multiply by 15, add 100, and figure out how many more acres he would have in the ground in that 8-hour time span. All right, so good. Very useful information. All right, well, let's try one more. And again, I am watching the clock, folks. I'm sorry to take so much time. All right, well, this one, Farmer Beige, which is sort of a relative there of Farmer Brown, is harvesting soybeans. All right, so a slightly different crop. But instead of planting, we're harvesting, so we're bringing them in. It says he started with 1,500 acres, so 1,500 acres to harvest. After 20 hours of work, there are still 1,040 acres remaining. All right, write an equation to represent Farmer Beige's situation. All right, well, notice it would seem that what we're measuring is the same thing. We're measuring acres, we're measuring hours, so let's just write that down. So independent this time is the number of hours that are being worked, and we'll call it x. And in this case, the dependent, slight change though, this would be the number of acres that we are planting, whereas this is still the number of acres. But in this case, it's the number of acres that have been harvested. So a big difference, especially if you're a farmer. So there's y. What's our rate of change? Well, I'm noticing something here. It didn't tell us. All right, it didn't tell us a rate of change. So let's see if we can figure it out. We know that he started with 1,500 to actually work with. So that would be 0 hours passed with 1,500 to do. All right, 20 hours later, so probably a couple of days worth of work at least. 20 hours and still has 1,040 acres remaining. All right, well, let's do a little math here and see what we find. So rate of change. I'm going to do, let's see, 1, 2, so 1,040, subtract 1,500 over, let's see, 20, subtract 0, and here we go. So if we take, now again, watch this. I really want y'all to understand this here. If we take the 1,040 and subtract the 1,500, notice that our answer comes out negative. Remember, we're harvesting. We're going to take so many acres and slowly but surely whittle them down so that we have fewer and fewer to harvest. So that's why our answer is coming up, make sure you can see it, that it's negative in this case. He is taking that many acres out at a time. All right, so we're losing acreage that we have to deal with. So negative 460 over, what do we say, 20? Cool. So let's divide that out. 460 divided by 20, and that gives us a negative 23. So he has 23 fewer acres every hour that he's working. All right, and 23 acres, guys, that's a lot. If you're doing that in an hour, my goodness, you must have a really big machine and you're flying fast. All right, initial value. Well, notice here we don't have to figure out what the initial value is. We were told up front he had 1,500 acres to start with. So 0, 1,500 that he needs to harvest. Cool. We're ready to write our equation. So y in this case is the number of acres that still need to be done. So y. Our slope, -23, so harvesting 23 acres an hour, where x represents the number of hours. So he's going to lose 23 acres per hour, and he started with 1,500. So again, where Farmer Brown could use this equation to figure out how many hours it would take to plant the fields, Farmer Beige could use this equation to figure out how much time it would take to harvest the full 1,500. Right? So that's what we're working on today. We're trying to generate these equations that we really haven't been able to generate before. And eventually, folks, we're going to be going back and forth between equations and graphs, or equations and tables, or equations and word problems at will. So again, we'll spend that time today practicing that skill, and you guys should be good to go. Have a great day.